Okay, welcome to the day of rice tables. Rice tables are the best invention on the planet when it comes to solving equilibrium problems. A few of the textbooks actually have started to put rice tables in there. So you'll like it. It's really easy and it's really simple. But what the point of using rice tables is to find either your equilibrium constant or your equilibrium concentrations when you're not given all that information. So let's look at this problem. The best way to learn it is just to jump in and solve. It says a 1 liter container holds 1.06 moles of H2 and 1.57 moles of CO at a temperature of 162. At this temperature, the following reaction occurs. So it's kind of like yesterday we started that fish tank business and we had a set amount of stuff, okay? And we're going to get to equilibrium. So now the reaction has to happen. So when I start and I just have these two things, and right when I put them together, do I have any product yet? No, so I'm not going to have any product at the beginning. After equilibrium is established, analysis shows 0.2 moles of CH3OH in the container. So once equilibrium is established, that's how much methanol was actually produced. Calculate the equilibrium concentration of this, and find the K. Can anyone tell me why I can't just plug all those numbers into the K expression? Because they're not equilibrium. This is not at equilibrium, and that is not at equilibrium. That's at the beginning, okay? The only equilibrium value we have is for the product, which is this 0.2. So because we need equilibrium concentrations, we have to use what we call a rice table. So R, I, C, E. What R stands for is reaction. So I'm going to go ahead and rewrite the reaction into the spots. Okay. Now, yesterday we did the equilibrium calculations using just the K and plugging in the equilibrium information. What two types of information can we plug into equilibrium? We did, what did the brackets mean? Concentration. So you can put concentration in this table. What else did I say we could do? Pressure. That is it. We can only do concentration or pressure. If you look, they've given us moles. We can't put moles in that table. We can only put concentration. But what's the good news? We're in 1 liter. So that kind of is the same thing as it is concentration, because we're going to divide all of those by a liter. So everything they're giving us, because it's in 1 liter, is concentration. So we're allowed to just plug this stuff into the table. I stands for initial conditions, whether it's concentration or pressure, so initial. And we're given that. We know the initial of pretty much all of them. So what do we know the initial concentration of H2 to be? 1.06 of CO, 1.57, and right when we mix those two, we've got nothing there. Okay, C stands for change. Change. And under that, I want you to write stoichiometry. We're going to have to see a shift in this reaction. The reaction is going to have to proceed either forward or reverse to get to equilibrium. How much it's going to change, we don't know right now. We're going to call it X, and it's stoichiometrically based on these coefficients. So which way do I have to shift to proceed with this reaction? I have no choice. We got to go to the right toward that 0. So we're going to lose some here, lose some there, and gain some there. You always go toward the zeros, okay? Now, how much do we lose or gain? Well, it's the ratio, 2 to 1 to 1. We don't know exactly how much, so we're going to lose 2x, lose x, and gain x. Don't worry about, students say, oh, we're losing 3 and gaining 1. That's not even. It's based on the balancing of the atoms, okay? So this is a stoichiometric ratio, 2 to 1 to 1. So that works out just fine. And the last E, what do you think E stands for? Yeah, equilibrium. This is going to represent, in this case, our equilibrium concentration, since we're putting concentration in. And so to get this last line, all we do is we add these puppies up. This plus 1.06 plus negative 2x is 1.06 minus 2x, 1.57 minus x, and this is just x. Now, in order to find these two concentrations, because the problem says we need to find CO and H2 concentrations, what do I need to solve for? I need X, right? Well, they did give me another piece of information in the problem. They said at equilibrium, I have 0.2 moles per liter of that methanol. So what does X equal to? 0.2. Perfect. So what I can do is take that X and plug it into each line. So I get 1.06 minus 0.4, and that comes out to be 0.66 here. So that's my equilibrium concentration of hydrogen gas. And then I'm going to plug in the 0.2, 1.57 minus 0.2 here, and I get 1.37 as this concentration, and we know this one, they told us. So there's our three concentrations. I've done part of the work. Now you have to, on the AP, indicate, you can't just leave it here and have me, the reader, look for your concentrations. You have to separately list, okay, the problem's asking me for H2 concentrations, so I know that's 0.66 moles per liter. The problem's also asking me for the CO concentration at equilibrium, and that's 1.37 moles per liter. It's also asking me for the K. How do I find the K? Good. I'm going to plug all of those into the equilibrium expression. So I'm going to go ahead and write the unsubstituted first, and I get products over reactants, H2 squared, times CO. And the reason I want you to write that expression is you might have missed that squared had you not done that. We got to square that H2. So we're going to plug in the numbers, and so we end up with 0.2 on top divided by 0.66 squared times 1.37. And let me know if I got this wrong, 0.335. Did y'all get that? Good. All right, let's move on to the next question. This says, a vessel initially has a partial pressure of NO equal to 0.526 atm and a partial pressure of Br2 equal to 0.329. Those are initial. At equilibrium, the partial pressure is 0.203. Calculate Kp. Why do we need a rice table? Well, I don't have all the equilibrium pressures. I only have one equilibrium pressure. So I'm going to be superbly lazy and just do my rice table like this. Right off the already written equation. Okay, so can we use pressure in the table? Absolutely, but we're going to be getting Kp when we do that, so just keep that in mind. So our initial concentration of NO, it says, is 0.526 atm. So I'm going to put that here. Right? And the partial pressure of Br2 is 0.329. When I put those in, and before they react, do I have any NOBr? No, they would have told us if we did. All right, so which way does this reaction have to shift? To the right. You always go to the zeros. Now, I think all the examples we're doing today are going right. Just know that if there's a zero on the left, you can go to the left. Reactions don't always go right. They're reversible. So we're going to lose, lose, and gain. How much are we going to lose? 2x. We're going to lose x, and we're going to gain 2x. That's based on the coefficients in the balanced equation. So when I add these guys up, I get 0.526 minus 2x, 0.329 minus x, and then 2x. Well, in order to get the equilibrium concentration, pressures, and to calculate Kp, because I need all of these equilibrium pressures to calculate that, I've got to find x. And turns out they did give me another piece of information. They told me the partial pressure of Br2, of this guy, is 0.203. Well, how's that going to help me? I'm going to solve for x because now I know 0.203 is equal to that equilibrium pressure of 0.329 minus x. So when we do that, I end up with my x being 0.126. Got it? So that's x. So now what I'm going to do is just take the x and plug it in wherever I can. So I've got my one equilibrium pressure here. So 0.526 minus 2x. I end up getting, check my math for me, I end up getting 0.274 for that one. And 2 times x for the last one, I end up getting 0.252. So those are my 3 equilibrium pressures. So now all I need to do, all they're asking for is Kp. Let me show you how to write a Kp expression with the pressures. You need to be really careful on the AP here. If you just put brackets, they're not going to give you the points. So what you need to do, Kp is equal to, you can put parentheses if you want, and brackets won't kill you, but what you have to do is write the P. You can't just put brackets and then the compound. You write pressure of NOBR. That's what you have to do. If you just write brackets NOBR, they're going to think you mean concentration. And then we're going to square that divided by the pressure of NO squared times the pressure of BR2 to the first. So that's our Kp expression. Same thing we've already done. So now we're going to plug stuff in, and we end up getting 0.252 squared divided by 0.274 squared times 0.203 to the first, giving us a final Kp of 4.17. Got it? Okay, let's move on to the next page, number 7. Well, it's the same page. Okay, we have a reaction, and 2 moles of HI are placed in 1 liter. Again, we're lucky that we're in 1 liter because we can treat that moles just like molarity, and is permitted to react. Equilibrium is found that, at equilibrium, it's found that 20% of the HI has decomposed. Calculate the Kc and the Kp. Right now, I just want to set up, initial, and do my change, and we'll worry about the 20% in a second. But in order to calculate Kc, and then we're going to swap that to Kp. What was that equation we used going from there to there? We did it yesterday. Politically correct. Huh? What did you say? Kc to the RT to the delta N. Changes no, political correctness changes no one. That's correct. All right, so let's go ahead and set up our rice table first. It's 2HI, I2 plus H2. These are all gases. I'm being a little bit lazy with my my notation, my state notation, but remember, if it's a solid or a liquid, say that this were a solid, for instance, we'd do this and we wouldn't even put it in the table, but that's not the case here. So this is a gas. So do I have any initial conditions? Did they give me any? Yeah, 2 moles of HI, and I've got that in 1 liter, so that's 2 molar. Are placed in a container and permitted to react. And if you put HI in a container by itself, it will react, and initially we had none of those. Which way does this have to shift? To the right, so we're going to lose how much? 2x gain, x gain, x. So we get 2 minus 2x, x, and x. Now here's the thing, and you can look at this one of 2 ways. You can say 20% decomposed or 80% remains. I like to look at it as the decomposed thing because we said 20% of the original left. What represents what left? This is what left, right? So 2x is what left, what's left. So that is equal to 20% of the original 2 molar. What's 20% of 2? 0.4. That's equal to 2x. Well, that's how much left. What does that do? How does that help us? It also tells us x is equal to 0.2. So now that we know 20% left, that leaves us with 2 minus 2 times 0.4, so that's going to be 1.6 here, leaving us, what are these x's? 0.2 and 0.2. Now, you might have thought, well, 80% remains. You could have done the same thing. You could have taken this little equation right here, and set that equal to 80% of 2. That would have been the same thing. Either way you do it is fine. So now we got to calculate KC. I'm going to do my unsubstituted equation. Products over reactants raised to the coefficient in the balanced equation. There it is. And so I'm going to substitute all my stuff in, and I get 0.2 times 0.2 divided by 1.6 squared. And so my final KC is going to be 0.016. Okay? But we're not done. We got to convert to KP. So that equation, we already said, was politically correct. Changes no one. So what was the thing I told you yesterday to always check first? Change in your moles of gas, because that's going to save you a lot of work. And sure enough, we have 2 moles of gas here, 2 moles of gas there. Products, these two, products minus reactants, that gives us a big fat 0. So if delta N is 0, that's going to get rid of this whole part of the statement. And so Kp equals Kc. You're going to, I got into kind of a tiff with one of the professors. They asked for to calculate Kp, right? Just saying Kp equals Kc didn't make them happy. You have to actually restate then that Kp is equal to 0.016. It's kind of redonkulous. And the reverse is true. If they say calculate Kp in terms of Kc, and you just say Kp is equal to 7, even though Kc is equal to 7, that's not the question. The question wants you to relate the two. So that would have been Kp equals Kc would have been the answer for that way it was phrased. So just be careful and listen to how they phrase it. Okay, this is a problem where we're actually going to be calculating all our equilibrium concentrations. This is a little bit different because if you look, they give us the Kc of the reaction. The Kc is 33.3. We want the equilibrium concentration. So what are we looking for on in the Rice table? That E line. We're solving for all the things on the E line. So let's go ahead and set up. And so we have PCl5 is in equilibrium with PCl3 plus Cl2. It says 0.4 moles of PCl5 are placed in a, 2-liter container. So what do we have to do to that 0.4? Divide it by 2, so we get, this is 0.2. Okay? And then it's told to go to, it goes to equilibrium, so we start with none of this. So in order for this to get to equilibrium, a right shift has to occur. How much do we lose? X, and we gain X, and we gain X. So we end up with 0.2 minus X, X, and X. Okay, that's all I have. And I've got the K. I know Kc is equal to 33.3. How am I going to find all my equilibrium concentrations? Anybody have any ideas? Perfect. Plug your X's. Plug everything on that E line into the expression and set it equal to 33.3. And we're going to solve. So like the pain in the butt teacher, I'm going to make you write the unsubstituted expression first because it's so much fun. So now what I can do is take everything, I'm going to change colors here, take everything from the E line and plug it in. So I get 33.3 is equal to X times X is X squared divided by 0.2 minus X. So this is when I get to say my famous math is hard, and we're going to have to do some math here. You are allowed to take quad form into the AP. I'll talk more about the fact that you probably won't have to use quad form for a number of reasons because you have an advantage with these calculators. And these calculators aren't a requirement on the AP. So until they do that, I believe they're going to give you equations where the X isn't in the quadratic formula. There's ways they can do it with square roots, and it makes it clean to solve. Or they might do something where you're allowed to drop x. We will be dropping x in Unit 11, not in Unit 12. So for now, you all have quad form, and we're just going to solve with the quadratic formula. So first thing I'm going to do is cross multiply here, and I end up getting, let's see, this is 6.66, right? Minus 33.3x is equal to x squared. So in order to do the quadratic formula, I've got to arrange my equation in such a way where I set everything equal to 0. I like my x squared term being positive. I don't know why. So I'm going to pull everything to the other side, and I get plus 33.3x minus 6.66. So at this point, you can plug this into quad form, and you're going to get two answers. So you should see two answers in your calculator. With the use of quad form, you should see negative 33.5, and you should see 0.1988. Those are the two roots. One of them is not going to make sense. Which one doesn't make sense? Negative 33, because you can't have a negative concentration. Now, sometimes you might get two positive ones. If you do, one of the positive ones will create a negative answer once you plug them into the E-line. So again, only one is going to make sense. So this is our x that we're going to use. So when we do this, we can now plug that x into our line and get all the concentrations. So I'm running out of room. I'm going to have to write small. But my concentration of PCl5 is 0.2 minus 0.1988. So that's 0.0012 moles per liter. The concentration then of my Cl2, which is equal to the concentration of my PCl3, is my x, which is 0.19. I'm being sloppy with sig figs, very sloppy with sig figs. I would have rounded everything to 3, so just ignore them for now. I'm more concerned about you doing this right. And that's how you do that problem. Okay, last one. It's going to be very similar to the other problem, but this time instead of one initial concentration, you're going to have two. So let's start with our rice table again. I'm going to write smaller this time so I don't run out of room. And so PCl5. And again, not all equations shift to the right. Tomorrow we'll do a few that shift the other way. Not tomorrow, Monday. Our initial concentration of this, we're still in 2 liters, so that's going to be 0.2 of this. And it says that, oh, we have 1 mole of Cl2, so that's 0.5 molarity of that. And we have nothing of that. We're still going to shift right because you still have to shift toward the 0. You can't make PCl5 without any PCl3. So we've got to shift to the right. So we're going to lose x, gain x, and gain x. So we get 0.2. All this does is make our math uglier, but it's not that bad. Okay? So there we go. We're going to set this equal to Kc is equal to PCl3. And like, oh, do you have to write it again? Yes. Okay. And now we can plug in and set equal to 33.3. We have PCl3 is x. This is 0.5 plus x. This is 0.2 minus x. So cross multiplying and distributing, I'm going to kind of do it all at the same time. I get 6.66 minus 33.3x is equal to x squared plus 0.5x. You all okay with me doing that? All right. And now we're going to combine like terms and get everything on one side. So 0 is equal to x squared. That's going to be plus 38.5, 0.3, right? 38.3x. 33.8, sorry. Math is hard. 33.8. And then minus 6.66. When you plug into quad form, the only root that makes sense, I got 0.196. Did y'all get that? Yes. So we're going to take that 0.196 now and solve for all of our equilibrium concentrations. We're going to have 3 different ones this time. So starting with PCl5, 0.2 minus that one is going to be tiny. It's going to be 0.004. And I'm just going to do 3 sig figs this time and be a good teacher. And then our PCl3 is the X. So that's 0.196 moles per liter. And then that PCl2, when we add it, we get 0.696. And those are all our equilibrium concentrations. So that is a crash course in rice tables. Y'all good in the hood? All right. So I have been corrected here that this down here, this is just Cl2. Concentration of Cl2 is 0.696. Bye-bye.